So in this video, we're going to be looking at pH and how we can calculate the pH of a strong acid and a weak acid as well, right? Now, to begin with, we know that pH actually describes how acidic or basic a substance is going to be. Now, so far, what we've actually looked at is a general acid, HA, and we've said that's going to dissociate and that's going to form H plus ions, and then it's going to form A minus ions as well. Now, when we look at the dissociation of our acid HA forming H plus ions, right, this is the key part which determines how strong an acid is going to be. Now, the greater dissociation of our acid to form H plus ions, the stronger our acid is going to be, because we end up with a larger concentration of H plus ions. Now, if we were to look at the concentration of H plus itself, right, because the numbers are so varied and so large, and we end up with negative powers and stuff like that, that means that it's quite hard and difficult to actually manage these numbers in calculations and when expressing ideas in chemistry itself, right? So what we can do is we can actually use the logarithmic scale instead, which gives more manageable numbers to work with, and we already know this as pH itself, right? Now, when we look at the pH numbers going from 0 to 14, each successive whole pH number, right, is a factor of 10 for the concentration of H plus. So we know going from, let's say, for example, pH 1 to pH 2, right, we've actually decreased by a factor of 10, right? We've divided by 10, going from 10 to the minus 1 of the concentration of H plus to 10 to the minus 2 of the concentration of H plus. And the same thing works all the way up until pH 14, where we know pH 14 is going to have a concentration of H plus being 10 to the minus 14 itself. So moving on, right, let's say if we were to calculate pH, right, how can we actually do that? Well, we need to be able to use the following equation where we do minus log of the concentration of H plus. And we can also use this equation to find the concentration of H plus as well, if we do 10 to the power of the minus pH itself, right? So there's two equations that we need to be able to remember. Now, when we deal with pH values, right, we always give them to 2 decimal places in calculations. And when we're dealing with the concentration of H plus, you've just got to be aware that if I were to deal with a dibasic acid such as H2SO4 or a tribasic acid such as H3PO4, so sulfuric acid and phosphoric acid, you need to look at the amount of H plus within these acids itself, and you would need to multiply your concentration accordingly as well. So let's start off with the first one, right? Calculate the pH of a solution X where the concentration of H plus is equal to 0.87 moles per decimeter cubed. So when we're calculating pH, right, all we do is we do minus log of the H plus itself, the concentration of the H plus, which in this case is going to be 0.87, and then we put that in our calculator, and what we actually end up with is a value for pH, 2 decimal places, as being 0.06 itself, right? What about the next example? We're asked to calculate the concentration of H plus, in this instance with nitric acid, with a pH of 0.5. So in this instance, what we're going to do is we're going to calculate the concentration of H plus, which is going to be equal to, right, 10 to the minus, right, pH, which in this case is going to be 0.5. I put that in my calculator and I end up with a value of 0.316 moles per decimeter cubed. And so there's my answer for that one. So yeah, moving on, that's how we calculate pH, right? What about if we were to calculate the pH of a strong acid, right? What if we were given the concentration of a strong acid and we were asked to calculate its pH? Well, we can make the following assumption that when we deal with strong acids themselves, we know that they almost completely dissociate, and so what we end up with is the concentration of HA, our general acid, being equal to the concentration of our protons itself. And bearing in mind, if we've got that assumption there, that means we can actually calculate the pH of given concentrations of acids rather than the concentrations of H plus instead. So yeah, if we look at the example over here, we're asked to calculate the pH of a 10 centimeter cube solution containing 2.3 times 10 to the power minus 3 moles per decimeter cubed of sulfuric acid, right? Now, in order to calculate pH, we need the concentration of H plus. In order to get the concentration of H plus, I need to get the concentration of my acid itself, which we can see is going to be 2.3 times 10 to the power of minus 3. We also need to bear in mind that we've got sulfuric acid, it's a dibasic acid, so in that case I know sulfuric acid itself is going to dissociate and form 2 lots of protons, and then that's also going to form sulfate ions as well, right? So in that case I can see my ratio is going to be 2 to 1. I don't need to mess about with moles over here because I'm dealing with the same volume, right? So yeah, if I were to start off, right, to find the concentration of protons in this instance, what I would need to do is I would need to take my value, my concentration, which is going to be 2.3 times 10 to the power of minus 3. That's my concentration of my acid, and I'm going to need to multiply it by 2, because for every 1 lot of acid we have 2 lots of protons. And so I do that and I end up with an answer which is going to be 4.6 times 10 to the power of minus 3, and that's going to be moles per decimeter cubed. So I've got my concentration of H plus. I can now find pH by doing the minus log of that. I do that, and what I end up with is a value that is going to be 2.33 in terms of its pH. You get 1 mark here and 1 mark here as well. What about the next one? We're asked to calculate the concentration this time of H3PO4 in a solution with a pH of 5 as well. So in this case, again, I'm dealing with a triprotic acid, and I have to calculate the concentration in this question. And so, right, I can start off by looking at phosphoric acid. It always helps to draw out the dissociation equation, and I end up with 3 lots of protons for every lot of phosphoric acid, and then I end up with a lot of phosphate ions as well. So in that case, my ratio is going to be 1 to 3. Now, if that's the case, right, we're working backwards here. So if I were to first start off by finding my concentration of H plus, which I can do by doing 10 to the minus of the pH, which is 5, I end up with a value which is going to be 1 times by 10 to the power of minus 5. And then I can find the concentration of phosphoric acid if I know that I've got a 1 to 3 ratio here. And so to do that, I'm going to take my concentration of H plus, and then I'm going to divide that by 3 itself. I divide that by 3, I end up with a value that is going to be 3.33 times 10 to the power of minus 3, and then it's going to be moles per decimeter cubed. Both of these units are going to be moles per decimeter cubed because we're dealing with concentration. So moving on, quick little task over here. Pause the video, have a go, and resume when you're ready to go over the answers. So in the first one, we're asked to calculate the pH of a solution of blood where the concentration of H plus is equal to 4 times 10 to the power of minus 8 moles per decimeter cubed. So in that case, I'm going to do pH is equal to minus log, and then the concentration, which is going to be 4 times by 10 to the power of minus 8. And then we're going to end up with a value that is going to be 7.40. And so there's our answer to 2 decimal places as well. Next one, calculate the pH of a sample of H2SO4, and the concentration given is going to be 2.01 times 10 to the power minus 2. That's of our acid. We need to find pH, so we need to find the concentration of H plus. So in that case, right, I can see that I've got a diprotic acid. So to find the concentration of H plus, I'm going to take the concentration of this strong acid and I'm going to multiply that by 2. So I end up with 2.01 times 10 to the power minus 2, and I'm going to multiply that by 2, and what I end up with is 4.02 times 10 to the power of minus 2, and that's going to be mole per decimeter cubed in itself. And now I need to find the pH now that I've got the concentration of H plus, and so I can work that out as being minus log to the base 10 to the concentration of 4.02 times 10 to the power of minus 2, and then I put that in my calculator, and what I actually end up with is a value of 1.4 itself. Right, so there's my pH, 2 decimal places, 1 mark here, 1 mark there. What about the next one? Calculate the pH of a 0.15 mole per decimeter cube solution of phosphoric acid. Well, looking at phosphoric acid, I've got a tribasic acid over here, so I'm going to need to multiply the concentration of my acid by 3, and so I'm going to have 0.15 times by 3. That gives me 0.45 mole per decimeter cubed for the concentration of H plus, and then I can find pH again by doing minus log of that concentration, which is going to be minus log of 0.45, and that's going to give me a value for 0.35 in terms of the pH as well. 1 mark here and 1 mark there as well, right? So yeah, moving on, right, 2 more tricky examples involving some quantitative chemistry as well. Pause the video and have a go. So looking at the first one then, we're asked to calculate pH of a solution containing 3 grams of HCl in 2 decimeters cubed. So starting off, I need to find the number of moles of HCl, which is going to be equal to the mass divided by the MR itself. And so what I'm going to do is I'm going to take 3, because that's how many grams I've got, and I'm going to divide by the MR of hydrochloric acid, which is going to be 36.5, and I end up with a value, after I put that in my calculator, as being 0.0822 moles. Once I've got the number of moles, right, I can then find the concentration of hydrochloric acid, which is going to be equal to, right, my number of moles divided by my volume, and that's going to be equal to 0.0822 divided by the volume, which is going to be, in this case, 2, right, it's already in decimeters cubed, and then we end up with a value that's going to be 0.0411, and that's how many moles per decimeter cubed I've got for my concentration. And then once I found the concentration of HCl, I need to use my assumption, which is the concentration of my H plus is going to be equal to the concentration of my acid, because it's monobasic and because we've also got a strong acid as well, so we end up with a complete dissociation. We can make that relationship there. So yeah, that's where I end up with. Then I can actually find a value of my pH by doing minus log to the base 10 of the concentration, which is 0.0411 mole per decimeter cubed, and I end up with a value of 1.39 itself for the pH. Get 1 mark here, 1 mark here, and then 1 mark over here as well. Next question is a bit more tricky because we're dealing with a dilution. We've got 5 centimeters cubed of a 0.025 mole per decimeter cubed solution of a strong acid, right, H3X. We can see it's tri-basic as well, and that's diluted to 100 centimeters cubed. We're asked for the pH of this solution. Now, to find pH, I need the concentration of H plus. To find the concentration of H plus in our diluted solution, I need to find the number of moles first in our undiluted solution. So I need to look at the following and work out the number of moles of H3X, and we know that's going to be equal to the concentration times by the volume, so that's going to be 0.025 times by 5 over 1,000, and I end up with the value that is going to be 1.25 times 10 to the power of minus 4 moles itself. That's how many moles that I've got. Now, thinking about my dilution over here, I've got 5 centimeters cubed within this beaker over here, and if I've diluted it to 100 centimeters cubed, the original number of moles in there is not going to change. We've just added water to it. So in that case, to find the concentration of H3X, right, what I'm going to do is I'm going to take the number of moles, which is still the same, divide by the volume, which is now different. So I'm going to have 1.25 times 10 to the power of minus 4, divide by the volume, which is now going to be 100 over 1,000. And so now what I actually end up with is a value of 1.25 times 10 to the power of minus 3, and then that's going to be mole per decimeter cubed as well. Now, as you can see here, I've got here concentration, which is a lot less concentrated compared to over here. Now, to actually find my concentration of H plus, what I need to do is I need to take that concentration of 1.25 times 10 to the power of minus 3. I could have done this earlier on as well, but I'm going to do it now. I'm going to times that by 3, and I end up with a value of 3.75 times 10 to the power of minus 3, and that's going to be mole and then per decimeter cubed. Remember that this is your concentration of H plus, and you times by 3 because it's tri-basic as well. Now I can actually find a value for pH, right, by doing the minus log of that. So I'm going to do minus log of 3.75 times 10 to the power of minus 3 as well. I'll put that in my calculator, and I end up with a value of 2.43 as my pH. I get 1 mark here, 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 and then finally here as well. So yeah, moving on, we've already looked at how we can actually calculate the concentration of H plus in strong acids and work out the pH of strong acids as well. And it's all based on this idea that strong acids, they completely dissociate in water, and so we know the concentration of H plus itself is going to be equal to the concentration of HA in this general equation for an acid over here, right? And so our calculations are pretty straightforward. Now, what about if we were to look at weak acids then? Well, weak acids, they only partially dissociate in water. And so if I were to look at HA, the concentration of HA itself, that is no longer going to be equal to the concentration of H plus, because when we look at the concentration of HA, right, hardly any of it dissociates, so it's going to be very high. And when we look at the concentration of H plus and A minus, the concentrations will be very low, because again, we know this dissociation is going to be in equilibrium, and we've got a reversible arrow over here. And let's say if I were to write an expression for this in terms of Kc, right, because that's what we can do, it's an equilibrium, I would have the concentration of my products over the concentration of my reactants. But remember, it's the concentrations at equilibrium themselves. We can actually modify this Kc expression to find the concentration of H plus and the pH of a weak acid itself. And we need to do that using two assumptions. The first assumption is that the initial concentration of HA, our undissociated acid, is going to be approximately equal to the concentration of our acid at equilibrium. Because if hardly any of this acid over here is going to dissociate, that means that the starting concentration, right, the starting concentration is going to be the same as the concentration at equilibrium. Now, if I were to look at the second assumption, right, based on the same idea, that means that we've got a very, very negligible amount of H plus and A minus, and if the amounts are so low, we can say that they are approximately going to be equal as well. So in that case, right, I can come up with a new expression which actually looks like this, where I end up with the concentration of H plus squared, and then that's going to be divided by the actual concentration of our acid itself. But now we can no longer call this the equilibrium constant, but instead we can call it a new constant, which is going to be called Ka, right? And what Ka actually is the acid dissociation constant. And like with other equilibrium constants, it varies with temperature. The units for this one is going to be moles per decimeter cubed, and this measures the extent of the dissociation of the actual acid itself. Now we can use this expression to estimate the concentration of H plus for a weak acid, but really we'd prefer to use something like a pH meter, just because sometimes this estimation might be off. And if you were to use the following approximation, right, that the concentration of A minus is equal to the concentration of H plus, and then our other approximation where we've got the concentration of our acid at equilibrium is going to be the same as the concentration of our acid undissociated, we can actually form this equation over here, and we can use this to calculate values of Ka, or we can rearrange it to find the concentration of H plus and hence pH, or the concentration of our general acid in itself as well. So let's look at an example then. Find the pH of a 0.02 mole per decimeter cube solution of propanoic acid at 298 Kelvin. The acid dissociation constant for propanoic acid at this temperature is going to be 1.3 times 10 to the power of minus 5. So I need to find the concentration of H plus and then find the pH itself, and I would need to rearrange this equation over here to get this over here. And so, right, I can say that the concentration of H plus is going to be equal to the square root of Ka times by the concentration of propanoic acid, which is going to be CH3, CH2, COOH. And so if I were to sub in my numbers, I would end up with 1.3 times 10 to the power of minus 5, and then that's going to be times in, right, 0.02, my concentration, square root it all. I do that, I put in my calculator, and what I end up with is a value of 5.09 times 10 to the power of minus 4 itself. And that is going to be in terms of moles per decimeter cube. That's a concentration of H plus that we've estimated. So yeah, to find the pH value then, what do I need to do? Well, I'll just do minus log of that. And so I'm going to do minus log of 5.09 times 10 to the power of minus 4. And then we take that, we put it in our calculator, and we end up with a value of 3.29 for the pH. You get one mark here and then one mark over here as well. So yeah, moving on, right, I've got a task here for you to do. Feel free to pause the video and have a go. So in this question, we're asked to calculate the pH of a 0.75 mole per decimeter cube solution of benzoic acid, which we can see the formula of over here. And we're told that the acid dissociation constant Ka is going to be 6.3 times 10 to the power of minus 5 mole per decimeter cubed. So the first thing is I need the concentration of H plus. I've got an organic acid here, which usually is going to be a very weak acid. And another hint that we've got a weak acid is that we've actually got a value for Ka itself. So in this case, right, I've got benzoic acid, which is C6H5 COOH, and that's going to dissociate, right, to form H plus, and then it's also going to form benzoate ions as well. So we've got C6H5 COO minus in that case, right? Now I can see over here that I've got a weak acid, and let's say if I were to look at my Ka expression, I would have Ka being equal to the concentration of H plus times by the concentration of benzoate ions, which is going to be C6H5 COO minus, and then that's going to be divided by the concentration of benzoic acid, which is C6H5 COOH, and so I end up with the following. So based on my weak acid approximations, I know the concentration of H plus is going to be equal to the concentration of A minus, because hardly any of our acid actually dissociates. And then I also know that the concentration of my undissociated acid is going to be the same as the concentration of acid at equilibrium itself, right? So in that case, right, I end up with a new equation, which ends up being the Ka, acid dissociation constant, being equal to the concentration of H plus, and then it's going to be squared divided by the concentration of benzoic acid So we can rearrange this, right, and we can get a concentration of H plus, which is going to be equal to the square root of, right, Ka times by the concentration of benzoic acid, which is C6H5COOH. And then if I were to sub in my numbers, right, I end up with the square root of 6.3 times 10 to the power of minus 5. And then that's going to be times by the concentration of my acid. I end up with a value that is going to be 6.87 times 10 to the power of minus 3, and that's going to be mole per decimeter cubed as well. Now once I've found that, right, I can actually work out a value for pH, and so that's going to be minus log of that value, so that's going to be 6.87 times 10 to the power of minus 3, and then that's going to give me a value of 2.16 for the pH itself as well. Now normally how the marks are actually given for this is they ask you for the K expression, they ask you to rearrange it and then calculate a value for the concentration, and then one for the pH itself as well. There's 4 marks available there. So moving on, right, I've got another one for you to try. Feel free to pause the video and have a go. So in this question, right, we're told the pH of ethanoic acid solution is going to be 3.02 at 298 K. Calculate the molar concentration of this solution. So we need to find the concentration of ethanoic acid, bearing in mind that Ka is going to be 1.75 times 10 to the power of minus 5 itself. So the first thing is we need to write out our expression for a weak acid. In this case, I've got over here ethanoic acid, which is a weak acid. I've been given a Ka value, so I know I'm going to need to do this as well. And I've got the concentration of H plus, which is going to be squared, and it's going to be divided by the concentration of ethanoic acid, which is going to be CH3COOH, like that there as well. Now I need to be able to find, first of all, the concentration of H plus, and I need a Ka value to find the concentration of my actual acid itself. Now I need to find the actual value over here for the ethanoic acid itself. How do I actually do that? Well, I need to rearrange this, so I get the following equation over here. I'm going to write it down below over here as well, which is going to be CH3 COOH. The concentration of ethanoic acid is going to be equal to the concentration of H plus, which is going to be squared, divided by the Ka value itself. I've got a value for Ka that's given over here. I don't have a value for H plus, but I can actually calculate that, where I can find the concentration of H plus, which is going to be equal to 10 to the minus pH, which is going to be equal to 10 to the minus, and then it's going to be 3.02. I put that in my calculator and I end up with a value of 9.5 times 10 to the power of minus 4. So in that case, I've got a value for the concentration and I've got a value for Ka. I can sub in these numbers, and so I end up with 9.5 times 10 to the power of minus 4, and that's going to be squared, and I'm going to divide that by the value of Ka, which is 1.75 times 10 to the power of minus 5. I'll put that in my calculator and I end up with a value of 0.052, and it's going to be mole per decimeter cubed. And so there is our final answer for that one there. So moving on to the next question, feel free to pause the video and have a go. So yeah, let's say if we were dealing with the following, we've got a solution of 0.162 mole per decimeter cubed of hydrogen cyanide, and it has a pH of 5.05. We're asked to actually find a value for Ka for HCN at 298 Kelvin itself. So here's the information we know. We know that HCN is going to be a weak acid because we've been told to calculate a value of Ka. So if I were to write an expression for Ka, right, here's what I would actually end up with. I would end up with the concentration of H plus, which is going to be squared in this case, divided by the concentration of HCN. And so if I were to actually look at what values I've got a value for the concentration of HCN, but I don't have a value for the concentration of H plus. Now I can actually calculate a value for the H plus concentration by looking at the pH itself. And so what I'd end up with is the concentration of H plus being equal to 10 to the minus pH itself, which is going to be equal to 10 to the minus 5.05. I'll put that in my calculator, and what I actually end up with is a value of 8.9 times 10 to the power of minus 6, and then mole per decimeter cubed as well. Now I've got that value over here. All I need to do is sub that in, so I end up with 8.9 times 10 to the power of minus 6, and that's going to be squared, divided by the concentration of our acid, which is going to be 0.162. We put that in our calculator and we end up with a value that's going to be 4.9 times 10 to the power of minus 10 mole per decimeter cubed. And so I know here I've calculated a value for Ka in this example. So moving on, looking at percentage dissociations, right? Some exam questions might actually ask you to calculate a value for the percentage molar dissociation of a weak acid, right? And all you're doing is you're taking the concentration of your actual H plus that you've got and dividing by the concentration of your acid that you started off with, times by 100 to express it as a percentage, and you end up with a value for the percentage dissociation. So looking at an example then, we're told that the pH of an ethanoic acid solution is 3.02 at 298 Kelvin, and we're asked to calculate the molar concentration of this solution and hence the percentage dissociation as well. Bearing in mind Ka for ethanoic acid is 1.75 times 10 to the power of minus 5 mole per decimeter cubed at 298 Kelvin. So again, we've been given pH over here, so we can use that to find the concentration of H plus. We've been given a value for Ka as well, and we need to find the concentration of our original acid and then find the percentage dissociation in this example as well. So in order to find the concentration of ethanoic acid, right, what I'm going to do is I'm going to take the concentration of H plus, which is going to be squared, and I'm going to divide that, right, by the value of Ka that I've got, but I need to find the concentration of H plus to begin with. So in that case, right, what I'm going to need to do is to find the concentration of H plus, I'm going to need to do 10 to the minus of my pH, which in this case is going to be 10 to the minus of 3.02. That's going to give me a value of 9.5 times 10 to the power of minus 4, and that's going to be mole per decimeter cubed. Once I've got that, right, I know that I'm going to have 9.5 times 10 to the power of minus 4 squared at the top over here, and then that's going to be divided by 1.75 times 10 to the power of minus 5. I put that in my calculator and I end up with a value of my concentration being 0.052, and then that's going to be mole per decimeter cubed itself. So there's our first part done. Now to find percentage dissociation, right, I need to be able to take the concentration of H plus, which in this case is going to be 9.5 times 10 to the power of minus 4, and divide by the concentration of my acid, which is 0.052, times by 100, and I end up with the value that is going to be 1.83% itself. So we know we only end up dissociating 1.83% worth of HA to form H plus ions itself, right? So yeah, you get a mark for calculating your concentration here, a mark for your expression, a mark for this concentration here, and then a mark for the percentage over here as well. So yeah, I've got an example for you to try. Feel free to pause the video and have a go. So in this example, we're asked to find the pH and the percentage dissociation of a 0.25 mole per decimeter cube solution of hydrofluoric acid, and the Ka of hydrofluoric acid, HF, is going to be 5.01 times 10 to the power of minus 4 mole per decimeter cubed at 298 Kelvin. Now the first thing that we need is an acid dissociation equation, and so I've got Ka being equal to the concentration of H plus, that's going to be squared, divided by the concentration of hydrofluoric acid, which is going to look like this. Now we need to find the concentration of H plus over here so that we can actually find the pH, and to do that, what I'm going to do is the square root of Ka times by the concentration of HF itself, because they're the values that I've got. I can sub in my numbers, and so I end up with 5.01 times 10 to the power of minus 4, and then that's going to be times by the concentration of HF, which is 0.25. We put that in our calculator and we end up with the value of 0.0112, and that's going to be mole per decimeter cubed. And then we can find a value for pH in that case by saying pH is equal to minus log of the concentration of H plus, which is going to be 0.0112 mole per decimeter cubed. I end up with a value of 1.95 for a value of pH, and so there's one of my values calculated so far. To find the percentage dissociation, right, I need to be able to do the following, where I take the concentration of H plus, which is going to be 0.0112, and then divide by the concentration of my acid, which is going to be 0.25. Put that in my calculator after times it by 100, and I end up with a value of 4.48% itself. So we know we've got weak acid over here, and we've got a very small amount of it dissociating as well. So moving on, right, what does Ka actually mean? Well, when we look at a large Ka value, right, we know that the extent of dissociation is going to be very large, and so the acid is going to be strong. A small Ka value indicates that the extent of dissociation is going to be very small, and so the acid is going to be very weak. So the larger the Ka is going to be, the stronger the acid will actually be as well. Now, sometimes we kind of end up with very small values of Ka, and just like with the concentration of H+, we can actually express them in their logarithmic form, known as pKa as well. Now there's two more equations that you need to remember, right? They're both the same one but just rearranged. We've got pKa being equal to minus the log of Ka, so that's how we can actually get a value for pKa, and then we can translate that back by doing 10 to the minus pKa to find Ka in that case. So we've got two equations here that we need to be aware of. Now if we were to look at pKa values, right, we say the smaller the pKa value is going to be, the stronger the actual acid is going to be, and we would end up with the reverse trend technically now of Ka itself. And so if I were to look at a bunch of different acids over here, I've got nitric acid, which is very strong, going all the way up until ethanoic acid, which is very weak. You can see the Ka value is going to be very large over here, but then for ethanoic acid, right, the Ka value is going to be very small. If we were to look at pKa, right, the opposite happens over here, where I end up with a minus value for nitric acid, and then as the strength of the acid increases, you can see the pKa value is actually going to increase as well. Now moving on, I want you to have got the following conversions for pKa and Ka, just some quick calculations to get your head around it. So yeah, in the first one, we're asked to calculate pKa of solution X if Ka is equal to 2.3 times 10 to the power of minus 1. So in that case, right, I know that pKa is going to be equal to minus log of my value for Ka, which I'm going to use circular brackets now, and that's going to be equal to, right, minus log of 2.3 times 10 to the power of minus 1. I'll put that in my calculator and I end up with the following value of 0.64 itself. So yeah, in that case, what if we're asked to calculate a value for Ka in the next question of solution Y, if pKa is equal to 7.2? Well, we know that Ka is equal to 10 to the minus pKa, which is going to be equal to 10 to the minus 7.2 in this instance, and so I end up with a value of 6.31 times 10 to the power of minus 8. Now in this next one, we're asked to calculate a value for pH of the solution HY, which has a concentration of 0.25 mole per decimeter cubed, and we're given a pKa here instead as well. Now straight away, to find pH, we're going to need the concentration of H plus somewhere, and we're told that the concentration is going to be of HY 0.25 mole per decimeter cubed. It's going to be a weak acid as well because it involves pKa, which we can find Ka from as well. So first thing is, right, we're going to need to find a value for Ka, which is going to be equal to 10 to the minus pKa, which is going to be equal to 10 to the minus 3.5, which gives us a value of 3.16 times 10 to the power of minus 4. Now I've got a value for Ka, I've got a value for HY, right? I need to think about my following equation. To find the concentration of H+, right, I'm going to rearrange my acid dissociation expression, and so what I end up with is the concentration of H+ is going to be equal to the Ka value, and that's going to be times by the value of my concentration of acid, which is HY, and then I'm going to do the square root of all of that, which is going to be equal to, sub in my numbers, I end up with 3.16 times 10 to the power of minus 4 squared, times by my value for the concentration, which is 0.25, and then I end up with a value of 8.89 times 10 to the power of minus 3. That's the concentration in moles per decimeter cubed of H+. Now I can finally work out a value for pH, which is going to be equal to minus the log of the concentration of H+, which is going to be 8.89 times 10 to the power of minus 3. And so I end up with a final value, which is going to be 2.05 for the pH itself. So all this is just an extra step in our calculations involving pH.